Oh yeah, getting some music going here, guys. Getting you pumped up. You a little pumped up there? You ready for some math? That's what I thought. You ready for some math? All right, let's do this. So that was my little music intro. I hope you liked it there. Now, let's get to some serious business of some geometry. Number one. Hi. Number one. We've talked about this before. Okay. Angle ACB. C is the vertex. It is on the center of the circle, so we call that a central angle. And this little guy out here, that's our partial circumference, well, we called that an arc. Okay, and what was the relationship between a central angle and an arc? They were the same in terms of degrees. Okay, so this is old stuff. Central angle, arc, same thing. Next up, though, is what if the vertex is not on the center, but what if the vertex is on the circle? Okay, then we're going to call this not a central angle, but an inscribed angle. And we have used this term inscribed before to talk about something being completely drawn inside of something. So we have an angle where all 3 points of this angle, A, B, and C here, are all on the circle. Okay, so this will be called an inscribed angle. Now this arc technically is called more than just an arc, but I will always refer to it just as an arc. But just in case you see this, technically it is called an intercepted arc. Now, what is the relationship between an inscribed angle and its arc, aka intercepted arc? The relationship actually isn't the same as it is for a central angle. The inscribed angle is half of the arc. So I might write this in a little short-term notation to say angle equals half the arc, to kind of remind me of what that relationship is. Now, why? Why is the inscribed angle half the arc? Now, we're going to kind of informally look at, we're not going to do a legitimate proof here, but it will be more of a formal proof anyway. We're just not going to have our 2 columns like we would normally do in a proof. Now, technically, there's 3 scenarios for this proof, and we're going to look at one of them. I'm not going to get into the specifics of each scenario, but we're going to show that this arc is, or if you took half of this arc, it's the same as this, inscribed angle, angle A. So here's what I'm going to do. I'm going to call that arc BC x. So I want to show that angle A is really 1/2 of whatever x is. All right. Now the first thing I want to do in my proof here is I'm going to draw in a radius from B to D. And why might I want to do that? Because now I have a central angle. And how big is this central angle here? It's the same as its arc, which is x. So now, how big is this angle right here? It would be 180 minus whatever x is, because these 2 angles together are on a straight line. In this case, they're on the diameter, and they must add up to be 180 degrees. So if this is x, what's left over is 180 minus x in this case. Now we're going to talk about this triangle in particular. There is something special about this triangle. It is so special, in fact, it has its own special name, because BD and DA are both radii of this circle, which means this is an isosceles triangle, which means that this base angle, angle B, or BD, or DBA, I should say rather, and this angle, DAB, are technically congruent to each other. Now in the end, I just want to know how big angle A is. Okay, so if I wanted to figure out how big angle A was, I need to think of the mathematical process of what I would do to get there using this one angle up here. So if you think about it, in this triangle there's 180 degrees. And I want to subtract away the one angle I know. Now technically I don't know the specific value of it, but I know its value is 180 minus x. So if I take 180 degrees, which is all 3 angles, and get rid of that angle, that would leave me with angle A and B left over. And I know that A and B are the same, so if I wanted just A, I would need to cut whatever this is in half. So this should be angle A. All I need to do now is simplify this. So really, there's an imaginary 1 between that minus sign and parenthesis, and I just really need to distribute that negative 1. So negative 1 times 180 is minus 180. Negative 1 times negative x is a positive x. Now look what happens here. 180 minus 180 will cancel out. And what's left over is x over 2. Now I can put a 1 in front of that x, and then what I could do is separate the number part from the variable part. So angle A in the end is 1/2 of x. And what was x? X was the arc. So we're saying again, the angle is equal to half of the arc, in this case, the x there. So that is kind of your informal, not really informal because we did it formally, formal proof. We just didn't do it very precisely with our 2 columns as we normally would with reasons. So the first example, we have to solve for 2 things here, x and y. Now, I'm going to start with the inscribed angle. Typically, I'll start with angles before I start with arcs, okay? So I know this angle is 49 degrees. Now, its vertex is at C. And I might do this, I might recommend you do this even, to see where that angle leads to. So if I look at where it goes to, and everything in between is its arc, which is this y. So I know the angle's 49, but what's the arc? Now, some of you might be able to easily get that, but let's say we've got the angle is equal to half the arc. Well, we know the angle's 49 though. So how are we going to figure out what the arc is? Just think of real quick, using some quick algebra here. If we want to solve for the arc, what if we multiply both sides by 2? So now the arc is equal to 2 times the angle. So arc is y, angle's 49, so 2 times 49 makes 98 degrees. So there's that piece. Now, x is another inscribed angle. So let's look at it. X goes all the way to A and all the way to D, and everywhere in between is its arc. Well, that's made up of 2 pieces. It's made up of the 98 and the 62. So what do I do with 2 arcs when I want to consider them as one whole? I would add them. So altogether, this arc is 160 degrees. If the arc is 160 degrees, the angle is half of that, so x is 80 degrees. Now for a few corollaries, and corollaries are like theorems in a way, but they come from other theorems, very similar theorems. So 2 inscribed angles that intercept the same arc are what? So let's just kind of look at this real quick. Angle A. Angle A goes all the way to B and goes all the way to C, and everywhere in between is its arc, which is that 160. Okay, so we could figure out angle A. Hey, that's 80 degrees, no problem. It's half of that. Well, we could also look at angle D, and D also goes to B and also goes to C, and everywhere in between is its arc, which is also the 160. So half of that, and that angle is also 80. So what's true about inscribed angles that use the same arc? They are, in fact, if you haven't figured this out quite yet, they are congruent. Oop, there we go. So it doesn't necessarily have to be 2 inscribed angles. It could be any inscribed angles that intercept the same arc, that use the same arc, are congruent. Number 2, an angle inscribed in a semicircle. Now, a semicircle is a half circle, which means we need to be looking at the diameter that's going to cut our circle in half. So here is a semicircle. And it's not necessarily the area on the inside, but the diameter with this half arc here, this semicircle. Since we have drawn in our angle here, and all 3 parts of this angle are contained within this semicircle arc, then how big specifically is this inscribed angle? Okay, so here's question mark, what is that angle? Well, how big is its arc? Its arc goes all the way from here to here. And how many degrees is that arc? Well, that's half a circle. There's 360 degrees in a full circle. So this is a 180-degree arc. So its angle is half of that. So it's got to be a 90-degree angle. So an angle inscribed in a semicircle is always going to be a right angle. Number 3, and the last one, the opposite angles of a quadrilateral inscribed in a circle. So when we mean opposite angles of a quadrilateral, I'm talking about angle A and angle C. They're opposite of each other. They are not adjacent. We could also say angle B and angle D. They are opposite of each other. And there's something special about these 2 angles and these 2 angles. So let's kind of talk about, without me giving you the answer up front, maybe what's going to happen here. So let's use Angles A and C as our example for our opposite angles. Angle A goes all the way to here and to here, and so here's angle A's arc, all the way from B, wrapping all the way around to D. Okay, do we know how big that arc is? We do not. So if we look at C, C goes from B also to D, but it doesn't go the same way around the circle. It takes up this much. Do we know how big this arc is? We certainly don't. But we do know that angle A and angle C together, okay, they're both inscribed angles. So inscribed angles A and C together make up how many degrees in terms of their arcs? Well, this arc plus this arc, well, that's all the way around the circle, which is 360. So if we apply the same reasoning that the angle is equal to half the arc, well, both of these angles should be half of their, or really of both of their arcs. And that is 360. And half of that is 180. So what did it mean for two angles to add up to be 180? I believe the term was supplementary. Yes, I put the emphasis on the wrong syllable. Deal with it. So example 2. Got two things solved for, x and y. Again, let me start with, notice y here goes all the way up to B and A, and everywhere in between is its arc, which is x. We don't know y, we don't know x, so we're kind of stuck there. But also notice that the 64-degree angle also goes from A to B and uses the same arc. So what's got to be true about the 64 and the y? Well, they have to be congruent. So y is 64 degrees. And if the angle 64, we said we would double it for its arc. So y is 128 degrees. Number 3, 5 things to solve for. VWXYZ. I'm going to start with the 80 because that's the only number I clearly see here. So if I take the 80, which is this arc from B to C, and then kind of backtrack to where it went back to. So I can follow it back to A, and I can follow this back to A, which is talking about this y. So again, the angle is equal to half the arc. If the arc is 80, the angle's 40. All right, now where? Notice here, AC, that's a diameter. It goes through the center, which means all the way around here is half a circle. Half a circle has 180 degrees, so V is 180 degrees. Notice angle X goes all the way up to A, goes all the way over to C, and goes everywhere in between. And how big is its arc? The 180, half of it is the 90. We could have also used that corollary because we have a inscribed angle within a semicircle. So we already knew this should be a 90-degree angle. Notice within this triangle, I've got a 90 and a 40, which makes 130 degrees, which means Z must make up the leftover 50 to make 180. Then, yeah, this problem's not done over yet. W uses that 50-degree angle as its inscribed angle, so it's double the 50, so W is 100. Okay, another way we also could have looked at that as 100 would be to say, hey, notice this arc here altogether. That's half a circle. That's 180 degrees. Here we've got 80. This must be the other 100. And then from there, you could cut the 100 in half to get that that angle was 50 degrees. Number 4, this uses the third corollary. We have a quadrilateral that is inscribed in a circle. So we said opposite angles were supplementary. So we know x and 102 must equal 180. So subtract 102 from 180 and get 78 for x. And the 84 and y, they must be supplementary. So subtract 84 from 180, and y is going to give me 96 degrees. Now just a kind of an FYI type term here. If you can draw a quadrilateral and inscribe it within a circle, you could call it a cyclic quadrilateral. If I can spell it right. Quadrilateral. Okay, so an inscribed shape. It doesn't have to be a quadrilateral, but it's called an inscribed. You could also call it a cyclic or cyclic, whatever you want to call it. One more theorem. The measure of an angle formed by a tangent. Now, tangent was that special line that touched the circle only in one spot, in this case at point C. So the angle between a tangent and a chord, here's that chord, BC. So they were really talking about this angle right here. So this angle is equal to half of its arc. And where is its arc located? What's trapped in between, which would be this guy here. So however big this arc is, take half of it, and that is our missing angle. So in this example, here's a tangent, here's a chord. So we got two angles going on here. We got the x and the y. So this angle x is equal to half of its arc, which is the 130. So half of 130 makes 65 degrees. So this is 65. Now, to get y, we can just notice x and y are together on a tangent line, which is 180 degrees. So y is just going to be equal to 180 minus the 65. So that's going to give me 115 degrees. And then I could say, all right, well, if I know the angle's 115, the arc's going to be double that. It's 230. And another way to look at it would be, there's only two arcs in this problem. There's this arc, which is 130 degrees, and there's this arc over here, which is unknown. Together, they must equal 360, so we could have also taken 360 minus 130 to get 230 for the z. Now, this problem is definitely not drawn to scale. Why does the 230 look like it's smaller than the 130? I should have secretly written up here, not drawn to scale, because I know some of you are going like, whoa, something's not right here. I don't understand. That doesn't make any sense. Does not compute. I just give up. Stop the video. I'm going to bed. Last example. Again, 5 things to solve for, A, B, C, D, and E. So if we look here, that 120 is looking pretty nice. 120 is from here to here. Where does it lead me back to? To angle B. And angle B is an inscribed angle. So the angle is equal to half of its arc. So B is going to be 60 degrees. Okay, 60, check. Now, clear off some of this here. One thing to notice in particular, one type of line are going to be diameters. Notice this diameter cuts the circle in half. If this much is 120, then how much is left over for E down here? E would have the leftover 60 to make a full 180. So E, 60. All right. We could do the same thing for D. Notice this, here's the other semicircle, which has 180 degrees. We have 56 right here, and then we have the D. So if we take 180 minus 56, D is 124. Okay. Now where to? Angle A. Take a look at angle A there. Where does angle A go to? It goes all the way to here, and everywhere in between is its arc, which is the 60. So half of the 60 makes 30 degrees for angle A, which also makes sense in another way because, let me clear some space off here. Notice this triangle, or more particularly, this angle, it's inscribed in a semicircle. And we said earlier this angle must be 90 degrees altogether. So if B was 60, we could have easily gotten that A must be the other 30 to make the 90. So there's something else you could have looked at. Now angle C. Angle C. This is a tangent line. Here's a chord. So this angle C is going to be equal to half of its arc, and its arc is the 124 at D. So half of 124 is going to give me 62 degrees for C. And that is it for this section. Good luck tomorrow in class with your homework, and I will see you during the next video. Sorry, I don't have like a music fade away. Like, yeah, we had fun. Yeah, party on. Adios.